The 8051, it can actually read the status of this, and it can read the status of this. Now, often they may give the same value, but they may not. It may be a situation where, as an output, you're driving this high, so you're trying to write a 1 out. This has gone low, so this is switched off. Now you're driving it as an output, you're testing this, so this is pulled up here, but you have a big resistor here, well, sorry, not a big resistor, a small resistor. Let's say you've wired this pin almost to ground. So forget about that, that was earlier, we've done that. So this time, I'm using this as an output, and I happen to have wired this pin to ground. And I'm writing a 1 into the queue here. Now, if you're writing a 1 into the queue, obviously you would expect the pin wants to be driven high. Why? Because this is high, means the output of the inverter goes low, which means that this transistor is switched off, which means that effectively you've got this pull-up resistor internally. So if this wasn't connected to anything, you basically have a pathway for VCC. But you've connected this pin, hardwired it to ground. So at this point here, the potential you would see is 0. So we have a situation here where you could test the output of the latch, and you would actually find the value 1, because we're driving Q high. But actually if you test the pin, because it's been hardwired to ground in this place, you wouldn't see the same value. Now you might say, well, why would I ever want to do that? Well, probably you wouldn't normally want to do it. But the point is, reading at this point and reading at this point don't always give you the same answer. There are different instructions in the 8051 for testing for reading ports. Some of the instructions will read the latch value, and some of them will read the pin value. I do not expect you in this course to remember which ones do which. But just to be aware that just because when you read a port, it says it's high, doesn't necessarily mean the pin's high, because you might be reading this one, the latch status. So some instructions will read the latch value, and some will read the port value. Now, they could be typically the same value, but if I've got this as an output and I've hardwired it to ground, it wouldn't be the same value. Yeah?
How can it be the same if it gets inverted?
What, without this thing here?
I mean, read here and read left.
Right, well, let's just not have this connected to anything. And let's say now that I'm driving this high. If I'm driving this high, Q's high, so if I read at this point, it's going to see a 1. Happy with that. The output of the inverter is low, which means this transistor is switched off, which means this transistor is not effectively there. But the resistor from here to VCC is pulling up that line to almost VCC. You've got an internal resistor here that's wired internally to, if you like, 5 volts. So in this particular case, where I've not forced this pin low or anything, if I was to read this point, I would also see a 1. Because basically, apart from this, they've also got this little resistor to VCC. So it's what it's called, it's functioning as a pull-up resistor. So if I read both the latch and the pin under those conditions, it would be fine. So, but there may be a situation where you want to test the pin and you're not sure if someone's hardwired it to ground. You could actually test for that, I suppose, because under those circumstances, even though this resistor is trying to pull the line up, you've just got basically a piece of wire all the way to ground. So there'll be a large potential drop across this pull-up resistor, but this point, the test point, will be at ground potential. And you'll get, basically then, this would read a 1 and this would read a 0. I mentioned that, like I say, in this course, I don't expect you to remember which instructions read the latch and which instructions read the pin. But to be aware that not all instructions, when you say, oh, I want to read that port, are actually reading the port. Some of them are reading the port, this thing, the actual pin itself, and some of them will actually be telling you what the latch is doing. And it's up to the program to remember which one's doing which. Okay, so in terms of instructions that work on the port, these are all different instructions that can be used to manipulate the port. Of those, which ones actually work on the pin and the latch, I think is on the next slide. Oh, no, it's not on the next slide. I'm just looking here. Right, so it's saying here in the small print, logic operations on the port will be operations on the status of the latch and not on the pin. So now, you know, basically if you do some kind of logic operation like complement the value of the port, that's a logic operation. What you're really doing is complementing the value of the latch, which may or may not complement the value of the port pin. It probably will, but if you happen to have wired the port pin down to ground, obviously it's not going to work. Okay. So these are various instructions that work on the ports. Those that actually operate on the latch and those that operate on the port pins themselves, I don't expect you to remember which ones are which, but to be aware that there is that slight difference. There was an exam question one year about this, by the way. This idea about why do you have to write a 1 to the port pins before you start using them as inputs. So that is considered core material. Okay, so we're going to move on to, we've finished assembly language programming now. That doesn't mean we haven't escaped it completely, but the kind of the basic building blocks, we've kind of left that to one side, and now we're going to look at, if you like, interrupts and timers. So let's get on with that. So I'll rather just do the slides. I think I'll do a bit of talking. But you must be getting sick to death of my voice, but anyway. Let's just do a summary of timers first of all, and then we'll start going through the slides. So inside an 8051, there are 2 timers, and those are known as timer 0 and timer 1. And they are both 16-bit timers. So, before you use too much, yeah, like that. So each of these 16 bits. From there to there. Most of the operations in the 851, although there are a couple of registers, and the timers are examples which are 16-bit registers, the accumulator is only an 8-bit thing anyway. And so to make life a little bit simpler, timer 0 is actually broken down into 2 chunks. And there's timer 0, timer low 0, I think it is, and timer high 0. Timer high 1 and timer low 1. And each of those are mapped into special function registers. So you'll find there's 4 special function registers with these particular names. Okay. So if you wanted to load a 16-bit value into one of these timers, where you could write, first of all, half of it to the low half of the timer and the other half to the upper half of the timer in 2 steps. You couldn't write from the accumulator a 16-bit quantity in one go, because the accumulator is only an 8-bit entity. So that's the first thing. 2 timers, each of those timers are 16 bits, and they have these particular, if you like, names associated with them. Also associated with the timers are 2 other registers, 2 other special function registers. One of them, which is known as TMOD, which stands for timer mode. And I think half of that deals with timer 0, and half of it is for, if you like, setting up the configuration for timer 1. And we'll look at that in more detail soon. There is also another register. This is an 8-bit register, by the way. So primarily its job, yep.
Could you say this again?
Yeah. So we have two 16-bit timers, known as timer 0 and timer 1. However, each of those 16-bit timers is broken down into 2 lumps of 8. And each of those lumps of 8 are identified by these names. So there's timer low 0, timer high 0, timer high 1, timer low 1. And they're the timers themselves. In addition to the actual timer registers, there is a special register, an 8-bit register called timer mode, TMOD. And I'm going to go into details of how we use this. But basically, this configures the timers to operate in one of 4 modes.
They connected to each other.
This controls how this timer gets incremented. So this is a kind of a control register that influences the behavior of these timers. And it's broken down into 2 halves. One half of it deals with configuring one of the timers, and the other half configures the other timer. There is another register as well, which is also 8-bit, called TCON, which stands for timer control, which is 8-bit. And in there, it includes a couple of flags, such as these ones. Timer run 1, timer run 0. Don't worry about the details too much yet, because we're going to see all the slides in a minute anyway. The TMOD register basically says how you want to use the timer. The T control register does things like switching it on and off. And it has some other useful features within it. Another thing I'll say generally about timers is associated with each of these timers, there is a flag. So there's a flag for timer 0, which we write as, and I think it appears in the TCON register. So there's a flag for timer 0 called TF0, and there's a flag for timer 1 called TF1, not surprisingly. And you might say, well, what do I need these flags for? Here's your timer, and you're, for example, putting numbers in here, and a typical role of a timer is to get it to count upwards. Okay? In the 8051, the timers, however it operates, the assumption is it counts upwards, not downwards. Okay? So you might initialize it with the value all zeros. I'm not showing you the whole timer here, I'm just showing you part of the timer. And then you could, for example, either based on the clock or based on some external input, you could get it to count upwards from that point. Okay? So, for example, each time you get some kind of pulse, you can get this to add 1 to what's in this timer. So it's just functioning as a kind of counter. Eventually, you will reach this count. Now I'm only showing 8 bits, but pretend it's a 16-bit thing, it's just I can't be bothered to write 16. When it reaches the maximum value, all ones, if you add a further 1 at that point in time, the timer will, what we call, wrap around and start counting from 0 again. But there is a crucial thing that happens once you go from everything set to 1 to everything back to 0. That triggers the flag to be set. So if this happened to be timer 0, at that wraparound point, TF0 would become high. So the flag basically is like an overflow flag. It tells you when the timer has reached the maximum value and you're going 1 more than that, which is causing an overflow. That sets this flag. That flag, we could use it ourselves to just test it. We could test the value of the flag. Or this flag can be wired into the interrupt mechanisms within the 8051. Now, I don't know how far I'll get with interrupts today, but effectively, what you can do if it was an interrupt is if this flag gets set, you could make your program go to a special place and do something special. Saying things in a very vague way here. But a typical example of using this timer would be something like this. To make life simple, I'm going to be using 8-bit timers. Remember, these timers really, generally speaking, are not 8-bit timers, they're 16-bit. But to make life simple, I'm dealing with 8-bit numbers here. So here's one of these timers. And let's say I've decided to drive it from the clock source. So remember, you've got your oscillator circuit. That's not how you spell oscillator, is it?
Yeah.
Is it?
Yeah.
However, anyway, those kind of pulses would be used to increment the timer. Now, if you are using the clock source, the clock itself does not cause the timer to increment. In fact, it takes one machine cycle to cause the timer to basically add 1 to whatever value is already in the timer. So, if you had, for example, a 12 megahertz crystal, you all know now that for every 12 clock cycles, we have 1 machine cycle in a classic 8051. So in a classic 8051, although the clock's doing 12 million things a second, the 8051, in terms of its machine operations, it's doing 1 million things a second. Or, if you like, 1 machine cycle is a millionth of a second. Okay? So 1 machine cycle equals 1 microsecond. So far, so good. If I change my clock frequency, these numbers will change, this number will change as well. Because the machine cycle is it's hardwired to the clock in the sense of for every 12 clock pulses, that's 1 machine cycle. So if you had a 16 megahertz crystal, the machine cycles will be different. They'll be smaller, they'll be less than 1 microsecond. However, let's assume we've got a 12 megahertz crystal, and that means that 1 machine cycle in this 8051 will be taking 1 microsecond. In order to add 1 to the counter, it takes 1 microsecond to achieve that. Okay? Because it takes 1 machine cycle to add something to the value that's in the counter. Let's say that I wish to know when 5 microseconds have expired. What I could do, if I think about that, let me think of a place to put it. I'll put it over here. 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. That transition will cause, in the timer, that transition will cause the flag to be set. Let's work backwards now from that. Remember, I want to basically create a delay of 5 microseconds. So what's 1 less than this one? So that's 1, 1, 1, 1, 1, 1, 1, 1. I'm just going to work backwards a minute. Just checking I've got this right, because mine. So, and let's do one more. I'm counting down, by the way, trying to anyway. So that's 7, 6, 5, 4, then it's going to be 3. If I was to load this value, let's just check I've got the right number. Might not have gone far enough. 1, 2, 3, 4, 5. Yes, I have. Let's say that I put this value into my timer. Okay? 1, 1, 1, 1, 1. That number. So I've loaded that value into here, and I've started the timer running. Let's think what happens. the timer's been told to start counting, doing its job. It's going to count up, and it's going to change every microsecond, because it takes 1 microsecond for it to add 1 to the count. So if I started here, 1 microsecond later, it will have added 1 to the count, and it will be here. Another microsecond later, it will be here. Another microsecond later, it will be here, the count. Another microsecond later, it will be here. Another microsecond later, it will be here, and this flag will be set. How long has it taken to achieve that? 1, 2, 3, 4, 5 microseconds. So typically, this is how we use the timers. We load some initial value in, and knowing how fast it counts, we can use it to create, if you like, delays of known amounts. Now, let's say I didn't want a delay of 5 microseconds, I wanted a delay of 6 microseconds. No problem. My initial value would be that, because it takes now 6 steps to get to the step that will cause the overflow. Yeah?
So how would you do it if you wanted it to be continuously every 5 milliseconds it'll be?
What you could do is when this happens, you can reset it back to this point.
But then that would take in...
It will, and you'd have to take that into account. That's true. So you might say, well, given that I'm going to reset it, and that's going to take a few machine cycles to do, factor that into this. Now, you might say, well, if it's a really small number, what can I do? There is no solution.
And you will have to reset TF as well?
Well, I'm going to come on to this.
Or you could just...
Usually, you have to reset TF, yes. Now, how do you know if TF has been set? There's 2 ways you can know this. The way that you're supposed to know so far is we can just keep testing it. We can just keep testing the value of that bit. When it goes high, we know the overflow's happened. Probably not today. Next week, we'll learn of another way of testing this, where effectively we can wire it into some hardware so that when it becomes set, it causes an interrupt. So we don't have to keep checking it. It will just automatically tell us when the overflow has taken place. But we won't be probably doing that today. Right, so it's 10 o'clock on the dot. What do you want, 10-minute break or 8-minute break or 20 minutes? I think we'll go for 10 then, as a compromise. So at 10 past 10 we'll start again and we'll just get on with the timer stuff.